Hi, this is Mike Mulholland, and today I'm going to be talking about the rules that are accepted as proving that triangles are congruent. So this is the question that I asked. I submitted the question. Explain why different combinations of equal angles and sides are or are not accepted as proving that triangles are congruent. And oh, by the way, this video is kind of long, but if you like geometry, I think you'll find it interesting. Anyway, I could have phrased the question better because I wanted to share some explanations that I had come up with for how the accepted rules work and how some plausible alternatives turn out to not work. But I'm not going to get into how to formally prove the accepted rules. I'm not going to change the question, though, because somebody else has already answered it, and it wouldn't be fair to me then to afterwards change the question. Okay, so here's the rules that are considered for proving that triangles are congruent. So when you see those rules, you might wonder why those work and why not angle, 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 why not side, side angle, because they kind of fit in there, and why hypotenuse leg is included when it doesn't sound at all like the rest, because its name doesn't have a combination of angle and side. I'm going to explore this first bullet point in this video, and then I'm going to give more detail on side, side angle and explain the second bullet point here in a follow-up video called Explain Side, Side Angle, Triangle, Congruency Rule. So what follows won't make much sense if you don't know what congruence and similarity are. Ideally, you'll have studied triangles and congruency and similarity before or be studying them now. But here's a very quick review to refresh your memory. Very informal way of looking at congruency is that for two flat shapes, if they're congruent, you could pick one up, move it, and or rotate it, and if need be, turn it clockwise or counterclockwise, if need be, even flip it over like a pancake, and then put it down on top of the other one, and the edges would exactly match. So these are all congruent to one another. To turn this into that, you'd have to flip it over. If you also had to shrink or stretch one of the shapes while keeping the proportions fixed before you could exactly align it with the other one, then the shapes are similar to but not congruent to one another. This triangle down here is similar to the ones up there but not congruent because it's got the same proportions but it's bigger. In my examples, I generally build from left to right with one side horizontal at the bottom, as you'll soon see. But my instructions leave that and many other things up to you, so you could come up with triangles following my instructions that look kind of different from mine or even from the one you did the day before. But they should be congruent, just not look quite the same like what we're looking at up above. All right, to decide whether a potential rule will always result in congruent triangles, we're not going to make multiple triangles and compare. That would be inductive reasoning. Instead, we'll think through making one triangle and see if there's any steps along the way that there's more than one way to do it that could result in triangles that are not congruent. So more deductive reasoning. So instructions below for constructing triangles are conceptual for how one could hypothetically create triangles from pieces you could move around. Intended to give some insight into possible congruence rules, don't have anything to do with classical pencil, paper, compass, ruler constructions. So we'll explore the rules for congruent triangles by building triangles from various combinations of sides of fixed or unfixed length. Fixed length side, unfixed length side, fixed angle, unfixed angle. By fixed, I mean specified for a single triangle or known to be equal for a pair of triangles that we're testing for congruence. And this red dot here is so that we can tell the fixed angles once we've attached sides to the angles and we don't have these arrows anymore. So many of these rules below will involve more than one fixed angle. And my first step in all such cases is to orient two of the angles. Actually, this is unfixed angles too. Orient two of the angles so that one arm of each angle is aimed at the vertex of the other angle, and the other arms are pointed in directions that could intersect. So this is okay. That's not okay. This would never make a triangle because this can't intersect with that. So angle, angle, angle. How would we build a triangle given three angles? Pick any two of the three. We don't need to use the third one. Aim them at each other, like I said. Put a side of unfixed length between these two vertices, and then extend unfixed sides here and here until they meet. And we did not need that third angle because automatically this is that angle, even though we didn't use it, even though we only used those two. Because it only takes two angles to define the shape of a triangle. Once you specified that, the third one is implicitly defined as well. You can see that visually here, also algebraically, because since they have to add up to 180, once you said what two of them are, the third one, you just have to subtract to get the third one. Now, in this middle step here, we did not say anything about the length of this side. It could be 3 millimeters, it could be 3 light years. So this triangle could be any size, basically. So that's why this particular thing, angle, 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 produces triangles that are similar, but not that you can trust to be congruent. So this one doesn't make the cut for those rules. It's not in the list for those rules. Since we only needed two out of the three angles, we didn't really need the third one, then you could think of that as being angle, angle, and then if you got two angles and a side, then you know more than you would for having just angle, angle. And so here's some, just following an angle, angle rule, different, you'll get similar triangles, but no guarantee they'd be congruent. All right, angle, side, angle is pretty similar to that one. How would you build a triangle given two angles and a side where the side is adjacent to both angles? So aim the angles at each other like before. Here's our starting points. These are the things that are given. But here's the key difference, is we adjust the distance between those two angles to fit the fixed side. Once you got the fixed side in there, then we put unfixed sides here and here and adjust their distance lengths so that they meet. And there's our triangle. So looks almost the same as before, but this side here is fixed now. So that one fixed side is enough to define the shape, the size of this thing. The two fixed angles define the shape. One side is enough to define the size. So this is going to produce congruent triangles, and it is in the rules of congruency for triangles. All right, angle, angle, side. How would you build a triangle given those? Two angles and a side that's adjacent to only one of the angles. The previous one was adjacent to both because the side was in the middle between two angles. So now what we need to do, we start the same as usual. We aim them. But what we do is we attach the one fixed side to the second angle in the name, angle, angle, side. So this side is adjacent to one angle, but not the other, and you got to keep track of which angle it is that it's adjacent to. And then you would adjust the distance between these until this is aimed at that. And then you would add unfixed sides in here, sides of unspecified length, to complete your triangle. So once again, 2 angles were enough to define the shape, and 1 fixed side, although in this case we have 2 of them, we only have 1, sorry. 2 fixed angles, 1 fixed side. The side defined enough to define the size. The 2 fixed angles are enough to define the shape. So this makes the list also. Side or angle side is one of the rules that's accepted as proving congruency. Now, those last two are kind of different sides of the same coin. 2 fixed angles define the shape. 1 fixed side defines the size. You could turn one into the other by just calculating the third angle and then using that in place of one of the other two if you wanted to turn angle side angle into angle side and vice versa. Now we also have side angle side and angle side, and this is quite different from that situation where here these are quite different, and you really need to keep track of the order of the parts in the name. Is the angle between the sides, or is it only at the end? So how would we build a triangle giving 2 fixed sides and the angle between them? So we attach the fixed sides to the fixed angle, like that, and then we just connect them with an unfixed side, because this is enough to determine the size and the shape of the triangle. So we only had 1 angle, but by having 2 sides, that was still enough to define the shape. And this works if the fixed angle is between the fixed sides. And so this produces congruent triangles, and it's on the list of things that are accepted as doing that. Side, side, side. You're not given any angles. Oh, and by the way, side, side angle should logically be next, but we're going to postpone it because it's the most complicated, but also interesting. So how would we build a triangle given 3 fixed sides? You'd attach them to each other end to end, and that's all it takes. There's no angles given, but if you've got 3 sides given, as you start to connect them, there's really only one way to do it, given the definition of congruency, that you may have to flip one over to make it match the other one. Okay, so again, this is sufficient to define the shape and the size. So this does make the list of congruency rules that work. Now, side angle, that's quite different. So it's a big mistake if you'd expect it to be pretty much the same as side angle side. The first one, side angle side, is about as easy you can get. This one is more complicated. So let's take a look. How would you build one? Attach the first fixed side to the second fixed side, keeping track of which is which in the name, because that's the one that gets the fixed angle attached to it. So 1 fixed angle, another one, and an angle. Attach the 2 fixed sides to one another. Attach the fixed angle. So now what we have is this length is fixed, but this angle is not. So this can swivel around. That's what this arc is showing, is swiveling that side around. And this side doesn't have a fixed length, but it has a fixed angle. So you can't change the angle on this black line. So you're looking for where would these guys meet? this arc and this black line. And look, two different places that this could meet. There's a possible vertex there, this shape, put this one down to here, pull it down to there. Where it meets that, you get that triangle. Or pivot this up to here where it meets the arc. Well, the tip is the arc. The arc meets the black line, and you get this triangle. So the two fixed angles define this shape, but you only have one fixed angle. And adding two fixed sides in this case is not enough to reliably define the shape when only one of the fixed sides is adjacent to the fixed angle. So either fixed side is sufficient to define the size if they had the same shape, but they can have two different shapes. So this does not reliably produce congruent triangles, so it's not included in the rules for congruency. But if you explore it further, there's some interesting things there, which I do look at in another video. Most often, side angle doesn't get considered any further than we just did, but it's interesting to do so. So I'll tell you about it and about the hypotenuse leg congruency rule, which we did not talk about yet, but is closely related to side angle. In another Ask an Expert question called Explain Side Angle Potential Congruency Rule. So I encourage you to give it a look. Thanks for watching.